All right, so you had a weekend of no homework hanging over your head, and something like that can't last forever. So here's a homework assignment, and it's actually due on Thursday, which is a quick turnaround, but the good news is this is the kind of homework assignment that's based on one lecture. So it's not going to be a lot of depth. We're just starting a new chapter, chapter 10, and I'm only going to have enough time to scratch the surface of some basic concepts. And so this entire homework assignment is based on some relatively easy, lightweight concepts. And so I don't think you'll have steam coming out of your ears like sometimes you do on a loop problem or a Darcy-Weisbach. So this should be hopefully an easy one. We'll talk about all the stuff you need to know to solve it. So it'll be due at the beginning of class on Thursday. Did everybody get a copy of the handouts? You need one? All right. There should be a few more coming your way. These are extras? Okay. Pretty obvious. All right. One quick hint is you're going to be solving Q equals VA a lot in Chapter 10 and Chapter 11. So just remember that relationship, that if you know the velocity and the cross-sectional area of a channel, then you can get the flow rate from that. Okay, so before we start digging into Chapter 10, let's talk about the project. In the email that I sent, I told you that we'd have some time to talk about the design project today. So as you looked at the map and thought about demand estimation, what questions have come up so far? Yeah?
Is there no fire flow needed for the east zone?
There isn't. And in fact, if you look at the summarization, I think there's only fire flow for the north zone. What?
North and south.
Is it on the south as well? Has anybody got a copy of the summarization? Yeah, it's only residential areas that have fire flows associated with them. So, yeah, north and south zone. Right. Other question? Yeah. As far as the weather is concerned, they're identical. Because what you need to know as far as the location is how much precipitation is going to be there. Like on a month-by-month basis. Because if during July there's only 1 inch of rain during the entire month, but your golf course needs 1 inch a week, so that means you're going to have to provide 3 inches out of the 4 required, and the rest 1 inch they'll get from rainfall. So pick whichever you find data more easily for. All right.
The fire flow equations, I think there was like 2 that were pretty viable. There was one that was like percentage of like the structure that was engulfed, and then there's another one that just had all units. Probably just use the one that's all units, so you don't have to.
I think I give you the fire flows directly on that spreadsheet. Yeah. In past semesters, I had students calculate the fire flows, and it requires you to figure out how closely spaced are the buildings, how tall are they, like what's their area. But that got to be a bit of a mess, so I simplified things and just said, here are the fire flows you need to assume. Mm-hmm.
I have a question on how to put this into water gems as far as like the ones that go into the north zone or out of somewhere. We put like a junction there, or how do we orient that?
Okay, so in water gems, you can draw the pipes anywhere you want to put them, but you have to have a junction at each of the letters. So you should have a junction at L, K, I, H. A junction should be, right. And then,
Connect them in the middle or anything.
what's that?
Like the ones that are going in, say, the north zone, for example, like the one coming off of A and then N, they don't have to connect in the middle or anything.
No. No, it doesn't have, so you're thinking in terms of maybe, well, we had loops in some of our homeworks. This doesn't have to be a loop. It can be just like a spur going to a single location. Yeah. Uh-huh.
I know it doesn't have anything to do with the demands, but when we actually go to get the elevations and everything,
Mm-hmm.
do we get the elevations from the points or from the beginning of the, like from the point?
Oh, yeah. So the arrow. The flat end, not the arrow end. So you're wondering, where is the spot?
Yeah.
Okay, so there's an arrow that looks like this. The spot is here. Yeah. Now, so you should get the elevation by interpolating between the contour lines. And in water gems, you can tell it the ground elevation and I think the junction elevation separately, but you can set them equal to, you know, like you could say the ground is at 700, but the pipe is at 695, and then it would be buried 5 meters under the surface. But you can use the ground elevation here, or you can say that it's buried a certain offset from the ground everywhere. Either way is fine. Other questions? Okay, so what's due by March 10th? So Tuesday, March 10th, you've got, well, that's a week from today. Okay, so a week from today, you need to figure out how much water is going to be coming out of each of these arrows. So the flow rate out from each arrow is what it boils down to. And to help you calculate that, I gave you the summarization chart. But let's talk about flow peaking just a bit. I don't use as much water at 3 a.m. as I do at 7 a.m. Why do you suppose that is? Why do you suppose I use less water at 3 a.m. than I do at 7 a.m.? Because I'm asleep versus showering, right? So if you think about my personal behavior and then you generalize that to lots of people. Some people wake up early, some people wake up late. In the evening, some people are washing their dishes by hand, some people are stacking their dishes in the sink, right? So this curve here is showing how water variation occurs during the day. And this is just for some town. This isn't like how it always is in every place. This is just, there's one certain town out there that has behavior that looks a little bit like this. And in that place, they have a morning bump of demand and then an evening bump of demand. And so we sort of get it, why the demand varies over time. So that's during the hours of a day. What this figure also shows is that in the summertime, people generally use more water than they do in the winter. And that varies a lot depending on where you are. You know, out west where they have to irrigate their plants and grass, they'll use a lot, there'll be a much bigger spread than compared to here where it's maybe a little tighter. We use some additional water during the summer than the winter, but maybe it's not as extreme. So this is showing the maximum day of the year versus the typical winter day. On the vertical axis here, that's saying percent of the average day. So if you think about on the average day of the year, maybe I use 400 liters of water on the average day. So that's, you know, if you add up all of my water consumption during the entire year, then that's how you'd find the average. The maximum day, there's some part of the day that I'm using less than that average flow rate, but then most of the day I'm using more than the average daily flow rate. And then here is the peak. So in your assignment for estimating the flow rates, you have to peak the average flow rate. And in the PDF that I provided on MU Online, where there's just a lot of different tables of how much water people use, you can find out on a per capita basis how much water people typically consume. But in that summarization chart, you have to peak it for the maximum daily demand and then the maximum hourly demand. And what we know is that compared to the average day is 1.0. Like if I use 400 liters per day, how many liters per second is that? Can someone divide 400 by 86,400? Because that's how many seconds there are in a day. Let's find that out in liters per second. Cassie, you're going to do that. 86,400. 400, that's all right. 86,400 seconds per day. So that's going to turn it into liters per second. Three times 10 to the minus 3 liters per second. Okay, so this is the this is the average daily flow rate, and okay, so that's the average daily flow rate. And what that means is that on the maximum day, so in July, if you multiply that by 1.8, that would be the average flow rate through the maximum day. All right? But then the maximum hour of the maximum day would be 3.25 times whatever this average daily flow rate is. And so, what's the most amount of water I'll use at any time on the maximum hour of the maximum day would be 4.63 times 10 to the minus third, and then times this peaking factor. And so you're going to be peaking certain things but not peaking others. And so look at this next, the forecasting summary table. So you can see the residential demand. Here's the average daily flow rate. You'll figure that up. Then you'll multiply it by 1.8 to get the peak day. And then you'll multiply the average day by 3.25 to find the peak hour. So the other thing you have to do is, over in this cell, add the fire flow and the peak day. So this cell plus the fire flow will give you this. So then the design flow is going to be the larger of this commercial peak hour plus either the peak day plus fire or peak hour. Which of the two is bigger is what you add it to. So let me say that again. The design flow is going to be the commercial demand peak hour, so this cell plus the bigger of these two. Okay? So that's what design flow is, and that's for the entire north zone. If we go back to the map, what you'll remember is that there's two different outlets providing water to the north zone. And so design flow rate per outlet, you simply divide it by 2. So the design flow, how much water are they using in the north zone? Deliver half of that water at junction A and half of the water at junction M. Okay? I think the most common mistake that I see is students will fill in the blank here. This is intentionally, this cell isn't filled in because there isn't a commercial demand plus fire flow. It's just the peak hour for the commercial demand plus the larger of those two cells is what you put in the design flow. All right. Some of the things you don't have to peak, like the golf course, I've had that, it's all blocked out because if they're smart at the golf course, they won't try and do all of their watering in 1 hour. All the watering for all of the courses in 1 hour. You think about, at the same time, you wouldn't want to spread it out over the whole day either, right? Because if you're watering the golf course during the hottest day of the year when it's sunny out, then that wastes a lot of water due to evaporation. And it also annoys the golfers who are getting wet. So you just put some logic and thought into, if you know how much water has to be put onto the grass to keep it wet, how many days a week are you going to do that and how many hours a day? And so you can find out what is the flow demand going to be for the golf course. A lot of this design is just based on your reasonable assumptions and thinking about, what's the worst case scenario and what do you want to just say it can't be more than this. Sometimes you'll have to not just go with the worst case scenario, but you'll say, well, we're just giving, in the case of the golf course, you're giving them a budget. They could try and water all of the grass in 30 minutes, but the pipe that will go to the golf course isn't big enough to allow them to do that. So if you have questions as you think through this, definitely feel free to stop by or send me an email and I'll do my best to respond. I have a spreadsheet where based on my reasonable guess, I know what flow rate I'm looking for each of you down here at the bottom. So I have a key, but I also know a reasonable range of assumptions And when I review what you've given me, I'll try and point out where I think, oh, well, maybe you're off track for the sports stadium, or maybe I'll think that your hospital demands are too high or too low. So the purpose of this being a draft submission isn't so that you can be like sloppy and relaxed the first time around. That's not it at all. It's so that I can take a look at your calculations, and if there's mistakes, you can fix them before the real high stakes end of semester grading happens. All right. If you do a bad job on the draft, I'll take off points. Okay, it's not just you get full points for whatever. I won't take off all the points if you make marginal errors, yeah. I'll try and be reasonable as I grade it, for once. All right. All right, well, Chapter 10. Here we are, open channel flow. You may remember this slide from fluid mechanics where we were talking about uniform versus non-uniform flow. And where we started off with when we were classifying flow is the idea that the velocity can either be fixed with respect to position in the case of uniform flow, or it can vary. And what you'll remember about non-uniform flow is that either the magnitude or the direction of the velocity can vary in order for us to consider it non-uniform. Since velocity is a vector, then that means that either its magnitude or direction constitutes some change in velocity. So here's a question. What type of acceleration causes non-uniform flow? Convective. That's right. So convective acceleration is defined as a change in velocity with respect to position. So convective acceleration is the cause of non-uniform flow. We also talked about steady flow, how steady means that the velocity is constant with respect to time, and unsteady means the velocity changes over time. So what was the kind of acceleration that causes unsteady flow? Local, right. So here's an example of unsteady flow, where at time equals 0, meaning at some certain time where we start measuring, there's water going underneath the road. There was a culvert under this road, but there were some problems with the culvert going under that road, and there was scour of the soil around the culvert, and as that soil got scoured, then the road started slumping, and eventually it collapsed, and you can see the flooding that was caused as the culvert's no longer able to convey the flow downstream. So here's a good picture that illustrates unsteady flow. We can't identify it with just a single image. It has to be a series of images over time. There's other ways that we can classify flow in addition to those two classifications. A channel is the shape of the container that water flows through in open channel situations when it's not under pressure. And by a prismatic channel, what we mean is something that has a regular cross-sectional shape. So typically an engineered cross-section would be trapezoidal or maybe rectangular. Those are the most common. A prismatic channel in side view means that the slope is constant. This brown line here is representing the ground slope, and then the red dashed line is representing the water surface. And so since we have a regular slope of the channel, you can see that the water slope is also regular. And they happen to be parallel in a prismatic channel. You know, we've got uniform flow if it's prismatic and if the flow rate is constant. Prismatic also means that in the top view, the channel isn't meandering. But contrast that to non-prismatic channels. We can have an irregular cross-section shape, and this is more like a natural stream or a river. It would be impossible for just by some miraculous occurrence, a river would be trapezoidal, where both of the slopes are the same. That just wouldn't happen. This is more typical of what a river cross-section could look like, and it's deeper in some sections than it is in others. There may be a floodplain when the water level gets above a certain depth. You can look that a non-prismatic channel may have variations in the channel bed slope. So this is looking in the side view. If you look at it from the side, sometimes the river is steep, sometimes the river is flat. And because the slope of the material is changing, that means that the water slope is also changing. The water will get shallower, it'll speed up when it's steep. And so the water slope is constantly changing in response to changes in channel slope. And then it may also be meandering and not just a straight channel. So prismatic versus non-prismatic. It's easy for us to calculate the depth and the flow rate for a prismatic channel. When we get into subsequent chapters and we start solving Manning's equation, we'll usually do that for a prismatic channel. In order to really understand what's happening in a non-prismatic channel, we have to use computer programs that break up this into little segments. It'll break up the cross-section into elements, meaning little rectangular slices, or it can break the channel into little segments where the slope is the same, and it basically puts cross-sections at intervals and then compares between the cross-section how things are changing. Sometimes I have students in senior design start to get into modeling of non-prismatic channels, but we won't do that in this class. All right, this is a really important table, and I was happy that one of you in the class has already found it. This is going to be something that you rely on a lot in this homework assignment and for the rest of the semester, table 10.7. So if you've got your book, maybe, like dog-ear the page, or I don't know, somehow make it visible, because you'll be coming back to it again and again. One thing I'll point out is it even has the formulas for a parabolic section. So what it says is for whatever the shape is, what the formula is for the area, wetted perimeter, hydraulic radius, top width, hydraulic depth, and then an indication of what the cross-section looks like. So I think in the homework you've got a rectangular cross-section that you'll deal with, a triangular, and a parabolic. What's an equilateral triangle? Yeah, each of the sides is equal. In an equilateral triangle, yeah, I know. What was geometry 8th grade, right? You're going to be dusting off that 8th grade knowledge a lot in the coming weeks. I never use geometry except for in this section of this course. So you're going to be like, okay, sine, cosine. Yeah, so in the homework, it mentions that there's a channel that's an equilateral triangle. And what that means basically is that it has a 60-degree angle, and the sides, each of the sides are the same. All right. And remember, I pointed this formula out to you, parabolic section. It's there. Table 10.1. Okay, turbulent flow is any time we have a Reynolds number greater than 4,000. But depending on how big the flow rate is, there's different types of turbulent flow. Remember when it was water flowing through pipes, we talked about fully turbulent. And fully turbulent was when the velocity was moving so fast that the F value only depended on the relative roughness, that it didn't really matter how much bigger the velocity got. There's a similar kind of a concept in open channel flow. So let's consider that we've got some river. Here is the bottom of the river. This is dirt. And the water is flowing to the right. Here's the top of the water. These little arrows indicate the direction, but they don't indicate magnitude, because what we know is that the water that's touching the dirt is moving slower than the water that's above and farther away from that resistance surface. And so this little curved line here, that means velocity profile. So the water is fastest at the top where it's touching the air, and the water is moving slow where it's in immediate contact to the resistance. Okay, so because there's a difference in velocity, down here, close to where the dirt is, the flow is laminar because we have a slow velocity. So that means that conditions in this small layer are laminar, and above that it's turbulent because the velocity is high. There's roughness elements, and the little jagged peaks there are meant to indicate how rough is the surface. And just like how we had different roughnesses for a concrete pipe versus a steel pipe when we were in enclosed conduits, there's also differences in roughness when it comes to open channels. Like if you have a channel that's lined with concrete, that'll be much smoother than a channel that has rock rubble at the bottom of it. So let's consider, in this case, the little roughness elements are in the laminar zone entirely. We call this smooth turbulent flow. And that seems like a bit of an oxymoron, right? A contradiction in terms. It's smooth turbulence. Anyways, that's what it's called. And what it means is that the roughness projections are submerged in the laminar sublayer. Transition is when, just by pure luck, the roughness elements are at the same height as the thickness of the laminar layer. And then rough turbulent flow is when the velocity is moving very fast, the bulk velocity in the stream. So what that means is that there's a very thin laminar layer. When you've got really high velocity, it compresses the thickness of the laminar layer to very small. So it may not necessarily be that these roughness elements are any bigger, but it may be that just the velocity is high, and so they're sticking out because of a thin laminar zone. So these differences are going to account for some of the variations in behavior that we see later on through the semester. All right, so let's consider an element of water. This little dashed line means we've got a control surface, and inside the control surface is a control volume, and enclosed within that volume is some water. So water is flowing downhill. This little cross hatching, that means dirt or a solid surface of some sort. It could be concrete. Here is the water surface. The triangle and the ripple marks tell us that it's touching the air. So the water, you can see, is getting shallower as it moves downstream. That may be because you're approaching like a waterfall. That's, in a case like this where the water is getting shallower and shallower, that's one of the typical causes, that there's some sort of it's getting steeper, or maybe it's losing slope altogether. So that's why it's getting shallower. But what this is meant to illustrate is we can do a force balance on this element of water. Consider the hydrostatic forces that are pushing on it to the right from here. So these arrows, that's reminding you that as you go down through the water, the pressure is increasing. Hydrostatic equation. So the pressure is increasing. If we've got some distance into the page, that gives us an area. And so pressure times area is force. And so there's hydrostatic forces to the right, hydrostatic forces to the left that are a little bit lower because the water depth is less. We also have the weight of the water acting downward. That's gamma times A times delta x gives us, A times delta x is a volume, times gamma gives us the weight of the water in that element. And then finally, you can see that there's a resistance here. This shear stress, tau, is related to the forces of this surface resisting the movement. So they're pushing to the left as the water flows to the right. So it's from this consideration of force balance, the momentum equation ultimately gives us a representation for the velocity of flow as a function of the roughness of the surface, F, and the slope of the energy grade line. Now, we won't actually use this equation very often. In fact, the F value, you won't see very much of that through open channel flow. F values and the Darcy-Weisbach method of estimating energy losses, that's almost exclusively for closed channel flow. In open channel flow, we'll start using something else to estimate energy loss. But we can make the relationship between the velocity of the water that's moving in an open channel and the F value and slope of the energy grade line. So there it is. There's three different slopes pictured on this diagram. This is important. You should put this off to the margins. You should draw what are the three different slopes. Okay, so the slope of this surface is S naught, slope of the channel. You can have a little tag coming off of it, S naught, slope of the channel. You can see that the water surface also has a slope. Now it's changing though, which makes it a little tricky. The slope of the water surface here isn't as steep as the slope of the water surface here. You can see that it's gotten a lot more steep. So the slope of the water surface is just at a certain point that we're going to pick that out. It's not constant like the slope of the channel is on this drawing. And then one more thing that we could put on here is the slope of the energy grade line. The energy grade line isn't pictured. Anyone want to guess where it would be? It can either be above or below the channel. It can be above or below the water surface. So where's the EGL? Where would the EGL be when we were working with the pipe network? It was above the pipe, right. It accounted for the elevation, the pressure, and the velocity. That's what the EGL was when we were thinking in terms of water flowing through a pipe. So here, it's about the same thing. We've got the elevation. Instead of pressure, we've got depth. And then whatever the velocity is at a certain point, above the water surface, there's the EGL. So we could draw a little dashed line, and there would be the energy grade line. It would be a dashed line above the water surface. And so whatever the slope of that dashed line is that represents the EGL, we're going to give that the variable S sub f. That means the slope of the imaginary line above the water surface. And it seems silly that we're having to, some imaginary line is what goes into all of our equations, but I guess it's only imaginary in terms of us being able to see the actual line. It's very real when it comes to what it represents. It represents the velocity head above the water surface. Any questions about this slide or what we've been talking about so far? Okay, so here's the comparison. I'll frequently try and remind you of some concept from pipe flow and then compare that concept to how it relates in open channels. So when we had the pipe flow, this is what the energy equation looked like. No surprises here. When we have open channel, here's how the energy equation gets transformed. Instead of pressure head, there's no excess pressure in an open channel. We're not pressurizing the water. And if you go down into the water, it has pressure, but that's accounted for with the Z component. So instead of P1 divided by gamma, we have Y1. That's the depth of it. You'll notice that Z1 and Z2 are accounted for, and so differences in elevation are accounted for in the same way that they were in the energy equation with pipe flow. And we still have the velocity head as well. But there is no pump in an open channel, and local losses aren't handled inside of this energy equation. When we have local losses, we're going to account for them separately. And like, what kind of a local loss am I talking about? Well, let's say we had water was flowing like this. This is a top view. If the channel got wider all of a sudden, then there might be some local losses associated with that. So when we start talking about channel transitions, we'll add the term that accounts for energy loss into the energy equation. But for now, this is what we mean by energy equation, is it's just the frictional losses are the ones that we account for, not the local losses. And there's no pump, no turbine. Okay? So really, here are the three equations that everything else is going to come from for the rest of the semester. Continuity, momentum, and energy. The momentum equation, what version of the momentum equation we use is called the Manning equation. rather than using the Darcy-Weisbach, and which relates the slope of the energy grade line to the velocity, the Manning equation relates the slope in uniform flow, so the water slope, the slope of the channel, and the slope of the energy grade line are all equal if we have uniform flow. Manning's equation says for some roughness value n, you can know the velocity by having a description of r, the hydraulic radius of the channel. We'll start using Manning's equation next week. The energy equation, H here, is referring to head, or the total amount of energy. So H1 just means the depth plus the velocity head plus the elevation above some datum at location 1. And likewise for 2. So everything comes from these three equations: continuity, momentum, and energy. So let's do an example here. We have at location 1, the riverbed, which is this thick black line, is above our horizontal datum, which is the dashed line. It's above it by 0.782 meters. The bed width, so that the width of this channel is 0.5 meters, and the velocity of the flow is 0.55 meters. The total energy is 1.451 meters. And so what I'd like you to do is calculate the water depth and the flow rate. While you're doing that, I'm going to hand back the 2 assignments that you submitted previously. And so feel free to collaborate with each other. And once I get those assignments handed out, I'll start putting the solution on the board. So we find the depth of flow, 0.654 meters. And then the flow rate, Q, is just the velocity that's given, 0.55 times the area. And now that we know the flow depth, we can multiply that by the channel width and find the cross-sectional area. And that's what gives us the flow rate Q of 0.18 cubic meters per second. So it's softball questions like this that's on your homework assignment. All right? Yeah. We all like softball, right? Okay, let me just bring up one point that I won't spend too much time on, but I do want to make you aware of. And that is that the energy equation actually, it is the depth of flow minus the cosine of the angle that goes into the energy equation. And the reason for that is that there is a difference between, okay, if we have a steep channel like this, the flow depth, here's the water surface, there's a difference between the vertical component of the depth and the component of the depth that is perpendicular to the flow direction. So water's going this way. So these two are going to have a similar length, but it's not exactly the same. So strictly speaking, the energy equation actually accounts for the cosine of the angle, where here's theta, but even when you've got a really steep slope, like even when it's a 10% slope, then this actual perpendicular length and the inclined length are 99.5% the same. The error is less than 0.5%, even when you have a relatively steep channel. And so we're going to, most of the time, just ignore the fact that we have the channel being inclined when we substitute in the flow depth. And so we'll assume that the inclined and the actual perpendicular length of the flow depth y are the same. And so that's another way of saying that this segment length L is very, very close to L times cosine of theta. Because when you have a small angle like this, then the cosine of that angle is going to be very close to 99.99%. And just to give you an idea of what's considered like a steep channel, around here where we have very steep topography, there is a channel that I'm working with right now for some research where it's got a 3% slope, and that's considered pretty steep. A 3% slope is a pretty steep creek. And so like a more typical slope, like a big mature river that has a lot of flow going through it, it would be like 0.1% or even lower. So this issue of inclined length versus horizontal length is going to be pretty minimal. But the book brings up the point, so I thought I'd mention it to you. One other important thing is that we're going to use a positive sign for downward slopes. We're just going to assume that, of course, the water is flowing downhill. So you don't always have to put a negative sign, like the minus, in front of your slope. We'll just take it as a given that our sign convention means a positive value is a downward slope. One of your homework problems asks a question about classifying the flow regime. And what they're asking for in that question is partly about, is the flow laminar or turbulent? And you already know how to do that. And you already know how to handle a non-circular conduit, because we talked about that for closed conduit flow. We said that instead of D in the Reynolds number, for example, you have 4 times the hydraulic radius, that you can make that substitution when it doesn't have a diameter because it's not a circular conduit. If it's a rectangular channel, then you, instead of putting D into a formula, you just have 4 times the hydraulic radius. But part of what that homework problem is asking about when it says what is the flow regime, they're also asking you to classify whether the flow is subcritical or supercritical. We don't get into this in a lot of detail until later in the semester, but just to give you an idea of how you can classify and determine whether the flow is sub or supercritical, is there's this formula that's called the Froude number. FR stands for Froude. And there's a lot of different ways to calculate it, but one of the easiest is if you know the velocity of the flow going through an open channel. This is the average flow velocity, V. And then there's something known as the hydraulic depth, Y sub H. And the hydraulic depth is just the area divided by the top width. T here means the top width. And so let me show you the implication of that. In a rectangular channel, the hydraulic depth and the actual depth are the same. So if you have a channel like this, and we've got some top width T, and it's got a cross-sectional area of, here's the depth Y. So area is T times Y here. And so Y sub H would be T times Y divided by T, so it's just Y. So obviously hydraulic depth wasn't designed with a rectangular channel in mind because they're the same. It's a trapezoidal channel. The hydraulic depth and the actual flow depth are different. So if we had some top width T in a rectangular channel, then you're going to calculate what's the area for this cross section and what's the top width, and then you'll get some Y sub H that it's basically what would the depth be if it was rectangular. It's sort of posing a hypothetical. If you had that same amount of flow in a rectangular channel, then what would its hypothetical depth be? So that's what we mean by hydraulic depth. So anyways, if you have a Froude number of greater than 1, that means supercritical flow. Less than 1 is subcritical flow. So put that as the criteria in your margin of the notes there. FR greater than 1, supercritical. Less than 1, subcritical. That's going to sound really impressive when you go home some weekend and tell your parents you've been studying supercritical flow. That just really sounds important, right? Supercritical. Not critical flow, supercritical. They're going to know that your tuition money is being well spent when you tell them that. And when you see supercritical, then you'll know that your tuition money is being well spent. All right. So you've got that table 10.1 either in the book or in the notes that I gave you. I'd like you to take a look at this and find each of the geometric parameters that I'm asking for. As you do that, I'm going to finish handing out the rest of these homework assignments. But at first glance, it kind of seems like impossible to know how deep the flow is, right? And at first glance, it seems like you don't have enough information for flow depth, but you do. So I'm going to let you figure out that puzzle. I'm tempted to give it away because it's so fun, but I'm going to let you figure that out on yourself, and then after I'm done handing out the homework, I'll start putting it on the board. So the depth, y equals 5 meters. And you know that just by looking at the side slope. If it's 2 to 1, that means these little side triangles have a top of 10 meters, and so that means that the vertical component of those side triangles has to be 5, since it's 2 to 1. Okay, area is b plus ty times y. So it's 15 meters plus 2 times 5 meters times y, which is 5 meters. Gives us 125 meters squared. Wetted perimeter, P sub w, the formula for that is b plus ty times y. Nope, I was looking in the wrong spot. All right, wetted perimeter is b plus 2y times w. And w is this special thing. W is 1 plus t squared to the 1/2 power. So let's calculate w to begin with. 1 plus 2 squared to the 1/2 power. So it's root 5, which is 2.2361. So that gives us the wetted perimeter is b, which is 15 meters, plus 2 times y, which is 5 meters, 2.2361. So the wetted perimeter is 37.4 meters. Hydraulic radius, R sub h, is area divided by the wetted perimeter. And that, so, is going to be 125 square meters divided by the wetted perimeter of 37.4 square meters. And it is 3.346 meters. Hydraulic depth, D, which we also called y sub h earlier in the slides. That is the A divided by B, the area divided by B, top width. So 125 meters squared divided by 35 meters. So 3.571 meters. And then finally, this section factor. We won't do too much with section factor, but it's fun to calculate it because we can. So A root D, 125 meters squared, square root of 3.571 meters. So it's going to have some interesting units. It's 236.2 meters to the 2.5 power. Okay. So that's just to give you a taste of how much fun we can have with trapezoidal geometry. When it really gets interesting is when the depth is unknown, when we're solving for the unknown depth. And you'll get a chance to handle that, not in this assignment, but in the next one. So I've kept you 2 minutes late. I'll pay you back those 2 minutes with interest next time. I always pay my debts. So I will see you on Thursday.